To start off this section of notes, we're talking about an explosion now. And I know you all have heard about an explosion, but in this class, an explosion takes on just a slightly different definition. In this class, all an explosion really is when two objects start out. Maybe I should put this over here. Say before the collision, two objects start out together. They're not necessarily locked, but they're together and they are at rest. Okay? And an explosion happens when in between the two objects there is a release of energy. Could be a physical explosion like a bomb going off or a gun that's fired. There's an actual physical explosion happens. And after the collision, afterward, the final part is that those two objects are then moving apart from each other as a result of that energy that's released in between, and they're moving in separate directions. Okay, so at the beginning, velocity is 0 of both objects. There's energy released in between them, and they begin to move off separate from each other in opposite directions. And that could happen in a number of instances. Most commonly, you'll find that this happens when there's a gun that's fired. Okay? When a gun is fired, you have two objects that are initially at rest, the bullet and the gun itself. The gun is fired, the bullet casing has gunpowder in it. It creates an explosion. That explosion releases the bullet to go off in one direction, and the gun itself actually moves in the other direction. That's why you'll feel a kick if you fire a rifle. Okay, so this is the definition of an explosion. It doesn't have to be a gun. It could be two carts that are, maybe two carts are stuck together, and perhaps there's a spring that's compressed in between the carts. That spring gets cut, it's released, and it propels the two carts then off in opposite directions. That's also an explosion. We can calculate it exactly the same way. So that's what the definition of an explosion is for physics. So, explosions. Let's work on this part of the notes. Again, it says in your notes there, any two objects that are initially at rest and then move apart as a result of energy that is released between them, that fits the definition of an explosion. The best examples are when a gun is fired, and I want to emphasize the firing part. When a gun is fired, and you can also say the carts moving apart example that I gave you. In an explosion, algebraically speaking, basically what is happening is that the total momentum of both objects initially must equal the momentum of object 1 plus the momentum of object 2 after the explosion, after the collision happens. Many things can be categorized as an explosion. These are the two most common. We can talk about a lot of different things. The cool thing about this explosion part is that the rho initial, the total momentum of the system, since it is at rest, for an explosion, and only for an explosion, the total momentum initially will always be 0. Always. You don't even have to do any calculation here. You can just throw a 0 in there. And that's because it's not moving. The other thing that you should remember about an explosion is that it's basically a locking collision in reverse. It's not exactly like a locking collision, but it basically is. It's a locking collision in reverse because a locking collision, you end up with one object. In an explosion, you start out with one object. Now, the difference is that in an explosion, we're definitely starting at rest every single time. With a locking collision, most of the time, this final momentum will not be at rest. Sometimes it can be, but most of the time, it's not going to be. So let's move into these practice problems. And the first thing I want you to do before I work one with you is to simply go through these, pause the video for a minute if you want, and simply categorize each of these as to what type of collision they are. All right, you've had a chance to look at it. The first problem specifically says, let's see, the ball moving collides with the second ball. After the collision, the velocity of the first ball is 0.25. What is the velocity of the second ball? The wording indicates that these two balls have two separate velocities after the collision, which means they are moving separately. There's two objects at the end, so that means that this is a bouncing collision. second problem specifically says that these toy engines lock together. That'll definitely be a locking collision. Locking collisions will specifically say that the two objects lock together or stick together. Here's another locking collision in the third practice problem. And the last one is a bullet that is leaving the muzzle of the gun. This is the firing of the bullet, and they're asking for the recoil velocity. That's the firing of the bullet, which gives us an indication that this is an explosion. In other words, you have these two objects that are at rest, energy is released, and they move apart. Just because you have a gun in the problem, though, doesn't necessarily mean that it's an explosion. It is possible to have a problem where a bullet that's fired actually gets embedded into another object, and the bullet and that object stick together and move apart as one object. That would be a locking collision. Okay, so just because there's a gun in the problem doesn't automatically mean that there's going to be an explosion. All right, so let's work this explosion problem together and see what we come up with. It's important that in some way, shape, or form you use the guess method to work these problems. You can use the algebraic method, which I'm going to be showing to you now, or you can actually draw a picture and put this together in table format, which I've done for you here. Okay, so you can probably figure out how to do that on your own. Right now I'm going to show you the algebraic method, which is basically the guess method proper. So guess method, I'll start. Let's just leave the problem here, and I'll start here with the guess method. G and U, the givens and unknowns. Well, if I look at this problem, bullet has a mass of 0.05 kilograms, and it's leaving the muzzle of a gun. The mass of the gun is 4 kilograms. The bullet has a velocity of 400 meters per second as it's leaving the gun. We want to know the recoil velocity of the gun. It's probably a good idea in this case to first draw a picture, which is kind of like the one that I drew for you up there on the board. Object number 1, object number 2. I'm going to call object number 1 the bullet and object number 2 the gun. Actually, maybe we should let's switch these actually, because that'll make our bullet velocity positive, which will be a little bit easier. So 2 is the bullet, 1 is the gun. That's before the collision. After the collision, they are moving apart. Object 1 and object 2, they're moving apart separately, 1 being the gun, 2 being the bullet. As far as what we know, I know the mass of object number 1 being the gun is 4 kilograms. I get that from right here. I know the mass of object number 2 being the bullet is 0.05 kilograms. What else do I know? Well, beforehand, I know that the initial velocity of both objects, initial velocity of object 1 and the initial velocity of object 2 is 0. It's pretty simple, but it helps to write it down. After the collision, they tell me that the final velocity of object 2, the bullet, is 400 meters per second. And they want to know what the final velocity of object number 1 is. Again, it doesn't really matter which one you call 1 or 2, or which one you call the bullet or the gun, as long as you keep your method straight. It doesn't matter. Alright, so I've defined what I'm given. They want to know the recoil velocity of the gun. So let's set up the algebraic part of this conservation of momentum problem. And that's basically this. Remember, we're looking at how many separate objects. So to begin with, I have one object, so I know that row total initially is equal to row 1 final plus row 2 final. Alright, and to flesh that out, that would mean that the mass total times the initial velocity is equal to the mass of 1 times the final velocity of 1 plus the mass 2 times the final velocity of 2. I know this side is going to be 0. I've already said that, but let's go ahead and put numbers in just so we can prove it to ourselves. Total mass is 4 plus 0.05, which gives us a mass of 4.05. That's the total mass of the system, plus the initial velocity of 0. That's why this whole side will initially go to 0. That's equal to mass 1, which is 4, times VF1, which is what I'm trying to find. Not equals, plus mass 2, 0.05, times velocity 2, 400. All right, so we have 0 over here, and that equals 4 times VF1 plus 0.05 times 400 gives me 20. The next step would be to subtract 20 to this side. I get negative 20 equals 4 VF1. And if I divide by 4, I find that the final velocity of object number 1, the gun, is negative 5 meters per second. It's a good thing we got a negative because the picture that we drew indicates that the gun is moving to the left. If I had drawn the picture the other way around, that's the reason why I switched it to begin with. If I had drawn it the other way around, that would have meant that I would have had to give the bullet a negative velocity. It still would have worked, but we would have gotten a positive final velocity. It may have made our math just a little bit more complicated. Not really that big a deal, though. So I want you to notice, first of all, that there's a big, massive difference in the velocities of object number 1 and object number 2. The gun is fired. You have a bullet moving at 400 meters per second. You have the gun moving the other direction at 5 meters per second. And the question I would ask you if we were in class is, why are those two velocities so different? And the answer lies in this information right here. The masses are so incredibly different. And if we go back to the illustration that we did at the very beginning of these notes with the dime and the quarter, higher mass, lower velocity, lower mass, higher velocity. Same thing here. The gun has much higher mass, much higher mass. So it has to have a lower velocity to compensate for the high velocity of the bullet. And here's the reason why. Remember that this momentum equals this momentum, and here's an interesting thing. The total momentum at the beginning is 0. That means the total momentum at the end also has to be 0. And the question now is, how can you have a bullet moving at 400 meters per second even though the total momentum of the system is 0? And the answer lies in the fact that the bullet is not the only one moving. The gun is also moving as well. And the momentum of the bullet to the right must equal the momentum of the gun to the left. In other words, the mass of the bullet times its velocity is exactly equal to the mass of the gun times its velocity. 4 times 5 is 20, and 0.05 times 400 is also 20. You have a positive 20 velocity and you have a negative 20 velocity. They exactly cancel each other out so that the total momentum is still 0.